Hi everyone, I'm Brad Sandford, Project Manager for Tunnels on Queensland's Cross River Rail project. Today we're here to talk all about tunnelling, including a brief history, a discussion on the complex engineering challenges that have to be overcome when planning and constructing a tunnel, and then some specifics around the tunnelling works on Cross River Rail. I'd like to start by acknowledging the traditional owners of this country. Public transport, it will also ease road congestion as more people choose to travel by rail. So at a glance, we're talking of 10.2 kilometres of new rail line, 5.9 kilometres of which is in twin tunnels which are travelling under the Brisbane River and the CBD. Along the tunnel, we are constructing 4 new underground stations. Along the full alignment, we are building 8 new upgraded stations and 3 new stations down towards the Gold Coast. And pulling it all together is 1 new world-class signalling system. The specifics of the tunnels. All the tunnelling activity this year is happening from the Woolloongabba work site, which is our main site for tunnelling, with all deliveries coming to this site and all the spoil being disposed of from this site. Our northern drive from the Woolloongabba station will be done by our twin TBM tunnels, approximately 3.6 kilometres in length. Our southern drive, 870 metres in length, twin mine tunnels will be constructed via road headers. Along the alignment, we will have cross passages at 240 metre centres, constructed via rock hammer or drill and blast excavation. A brief overview of the alignment vertically of Cross River Rail. You can see our 4 stations here, travelling from Boggo Road, Woolloongabba, Albert Street, Roma Street, through to our northern portal near Normanby. At the deepest point under the Kangaroo Point Cliffs, the tunnel is approximately 58 metres below the surface. Where we travel below the Brisbane River, we will be approximately 42 metres below the river. Albert Street Station is our deepest station at 33 metres. So, what's a tunnel and why do we need them? What I consider to be my definition of a tunnel is an artificial underground passageway that allows the movement of something from where it is to where it needs to be, when the alternative surface route would be too difficult, too invasive, or too slow. So tunnels are about facilitating movement, be that the movement of people, vehicles, freight, or essential services, such as water and electricity. And it's about moving those things without disrupting people at the surface. You can imagine that if Cross River Rail was a surface railroad and we were putting it through the CBD, that would be quite disruptive. So now that we have established what a tunnel is, what are they used for? Well, tunnels have a myriad of applications in our daily lives, be that tunnels that are used for utilities, getting gas and electricity around to where it's needed. They can be a pedestrian route, providing safe crossings under major roads in the form of pedestrian underpasses or connections through underground subways. They support the transport of rail and metro systems in all major cities across the world. We see road tunnels everywhere, providing traffic a free pass from traffic lights and passing otherwise congested areas. We have water and wastewater tunnels, and tunnels that are also provided for flood prevention and also to supply desalination plants. Tunnels are even in the realm of energy generation when adopted into hydropower stations. And just recently, we have seen that Norway has announced they're going to build the world's first ship tunnel. So tunnels really are being used for everything. But how did we get to this world of tunnels? Throughout history, tunnels have also served other purposes. In ancient times, underground excavation was mainly used for burial and religious purposes, followed by construction of drainage, water supply and sewers. And impressively, a number of these ancient structures still stand today. The image in the top left is an ancient tunnel which is located in central Turkey, believed to be from the 7th or 8th century BC. Ancient Babylon built tunnels for irrigation, and both ancient Greece and the Romans used tunnels or underground aqueducts for water supply and drainage. During the 17th century, canal tunnels started to be constructed in France, and later across Europe, the UK and North America. As water transport gave way to rail in the 1830s, these canal tunnels were replaced by the construction of rail tunnels. In the 18th century, more advanced tunnelling construction began. Drill and blast excavation using black powder was adopted, and formal tunnel support in the form of timber structures. Tunnel linings were also implemented, often using bricks and cement. Tunnels were also constructed to support the mining of coal, which was a key driver for the Industrial Revolution. Historically, these early tunnels were constructed in rock due to the inherent support that the rock mass provided. But with the growing metropolis of 18th century London, the need to provide a crossing below the River Thames was being given a lot of consideration. But to date, the thought of tunnelling under rivers or bodies of water was considered impossible. What resulted was the development of a tunnelling shield that is shown here in 1818 by French engineer Marc Brunel. This shield was first used in 1825, supporting the ground in front and around it as they excavated through clay soils under the Thames River. The project encountered several difficulties along the way, such as flooding, worker deaths, and a 7-year shutdown that was needed to secure refinancing for the project and building of a second shield. But the world's first underwater tunnel, or subaqueous tunnel, was completed in 1841, a 16-year period, or 9 years of construction if ignoring the shutdown period. This scared people off using shield tunnelling for several years, until 1869 when Peter Barlow and James Greathead developed an alternative shield prototype that used a circular shape and installed a lining of cast iron segments. In 1874, James Greathead further improved on this concept by introducing compressed air to create a pressurised chamber at the front of the shield that was used to counter the outside water pressure. This was known as the Greathead shield. The first major application of the tunnel shield plus compressed air technique occurred during 1886 on construction of the London subway. This achieved 7 miles of tunnelling works without a single fatality, a momentous achievement. And this cemented the role of tunnel shields as a safer and more effective way of tunnelling, allowing tunnelling projects to take off and facilitating a boom in rail and subway tunnel construction in major cities across the world. Building off this shield concept for safer and more efficient tunnelling, further innovations were introduced in the first half of the 19th century, including compressed air rock drills, dynamite for excavation, formal lining designs, the introduction of formal tunnel ventilation systems, and improvements in survey control that all helped revolutionise tunnel construction. These new methods allowed tunnel construction under conditions which up to this time were not accessible for safe or effective tunnelling. In 1954, Jerome Ackerman, F.K. Mitry and James S. Robbins successfully trialled the first mechanical rotary excavator for tunnelling, known then as the Mitry Mole and now commonly referred to as a tunnel boring machine or TBM. Further developments occurred through the 1960s, with significant developments in geotechnical engineering and subsurface explorations emerging that allowed ground behaviour to be modelled and predicted, with these predicted effects confirmed through field observations. This led to the development of formal ground support systems, which led to the modern era of tunnelling, which we consider began in the 1970s. So I've convinced you now that tunnels are awesome. How do you go about getting one? Well, before we can go digging, there are many considerations that need to be addressed when it comes to planning a tunnel. and each of these items will serve to drive us towards the type of tunnel to be constructed and the subsequent method or methods of construction. One key factor is the alignment of the tunnel, both vertical and horizontal. How long the tunnel needs to be is also a key factor, and ensuring that sufficient ground cover is provided to support the tunnel, but also mindful of the fact that as tunnel depth increases, they also become more challenging to construct. And along this alignment, how do we get access to the tunnel to construct it? Do we have space at either end for construction compounds? Do we have intermediate access requirements for operational or construction needs? What is the purpose of the tunnel? There is no point building a rail tunnel that doesn't fit a train, or building a road tunnel that only allows for 2 lanes of traffic when the volumes require 3. What are the key safety concerns and risks that we have with the proposed tunnel? Can we improve on these if we tweak one of the other areas? What are the constraints along the alignment? Is there sensitive structures? Is there zones that need to be avoided? Is there a river crossing? Groundwater. Do we have zones of high groundwater pressure that will impact our tunnelling? Do we have a high risk of inflows during construction so that we need to adopt a construction approach that can safely and effectively manage this? What about our ground conditions that we encounter along the alignment? Are they favourable to tunnelling, or will they be challenging and result in excessive support requirements which cost us time and money? And cost. The longer a tunnel, the deeper the tunnel, the heavier the support of the tunnel, the more it costs. Is it cost effective to build the tunnel? And community. Is there community issues that need to be considered? Tunnelling can have noise, vibration and dust impacts, and these must all be managed. And can we do that better by changing one of the other factors? For relatively large cross-sections of tunnel, 3 basic construction methods are available. We have bored tunnels, cut and cover tunnels, and immersed tubes. For each type of tunnel, a whole range of different methodologies for construction can be chosen. For cut and cover tunnels, the tunnel structure is excavated between pre-constructed walls, usually constructed through piling, and finished with a roof structure which is subsequently backfilled over. 2 methods for cut and cover construction exist. One is bottom up, which is done by using an open cut excavation and then building the permanent structure back up to the finished surface. Top down construction involves the construction of a roof, with the subsequent excavation and permanent structure installation taking place underneath this. Cut and cover tunnels are often associated with the beginning of driven tunnels, known as the portal, and where the launch of the driven tunnel works generally commences. They are also used for shorter lengths of tunnel, or where ground cover is insufficient to allow driven tunnelling to occur. Cross River Rail is constructing cut and cover tunnels at both ends of our tunnel that will be used for retrieving our TBMs at the north and accepting our road headers driving south to Boggo Road. Immersed tube tunnels. These are used for generally crossing rivers or for sea channels. They are assembled from prefabricated segments which are floated to the intended location, sunk into place, connected and then sealed. These segments are generally steel or concrete. Immersed tube tunnels are often associated with a cut and cover or a driven tunnel, with the immersed tube tunnel being used in the underwater section and then connecting to land via cut and cover or driven tunnel elements. And finally, the main focus of our discussion today are the bored tunnels. There is a range of construction methodologies associated with bored tunnels, chosen based on the parameters we discussed earlier. They include using a tunnel boring machine, or TBM, or adopting the new Austrian tunnelling method, also known as NATEM, and also considered sequential excavation method. On Cross River Rail, we are adopting both TBMs and NATEM. Our TBMs are driving north from Woolloongabba, and NATEM is being used to construct the tunnels south to Boggo Road. These tunnel boring machines, the modern versions of those original tunnelling machines, are amazing feats of engineering, and you can see them for our Cross River Rail project in these following images. So these are our TBMs for Cross River Rail, TBM Elsa and TBM Merle. They're a dual shield TBM with closed mode operability. They have a nominal 7.2 metre diameter, and as they go, they will install their precast concrete lining segments behind them. Each TBM weighs approximately 1,350 tonnes, is 165 metres long, and will operate 24/7 by a crew of 15 workers. Our TBMs were assembled at the WestConnex facility in Brisbane, and from there were moved to the Woolloongabba worksite in December 2020. The TBMs being used on Cross River Rail are reconditioned TBMs that were used to excavate the Sydney Metro project. After Sydney, they were sent to China, where their cutter head and front shield were repurposed for Cross River Rail, and then they were sent back to Brisbane. Once here, they were assembled and tested in the WestConnex yard, then they were disassembled and moved to Woolloongabba. And here is TBM Elsa, ready for launch at the Woolloongabba site, which she took off on her journey in February this year. So now that we have chosen our tunnel type and excavation method, we need to work out a way to make it safe to use and not collapse. And we do that by installing tunnel support. In tunnelling, we can differentiate the stages of ground support into two types that are installed at different times. Our first stage, our primary support, is the temporary support installed when the tunnel is first excavated and makes the excavation safe for workers and to allow subsequent excavations to continue. This is often a combination of rock bolts and shotcrete, which is sprayed concrete, but can also involve the use of steel mesh, lattice girders, or steel beams. The second stage of lining, our secondary lining or permanent lining, is our long-term tunnel support that takes care of long-term durability, waterproofing, loading and operational needs of the tunnel. Generally, this is a cast in situ concrete lining system, but recent tunnels have been adopting shotcrete also as the permanent lining. In TBM tunnels, the lining is a single pass system. Our precast concrete segments are installed in a ring behind the tunnel, and they provide both the temporary and permanent ground support in one pass. The support for a tunnel is designed and implemented based on a number of factors, which includes the tunnel profile and the cross-sectional area, the depth of the tunnel, the ground conditions expected, and any surface loading that may be experienced by the tunnel, now or into the future. Other considerations, such as the location of cross passages along the alignment, also need to be considered by the support design. Another key component of the support system is the excavation sequence. When we are excavating, we need to ensure that we are not cutting too far in front without having appropriate support installed. In favourable ground conditions, we can advance further without stopping to install our primary support. But in soft or unfavourable ground conditions, we would need to be installing our support more frequently, as the rock mass is not capable of self-supporting itself for any length of time. Regardless of the method chosen, TBM or NATM, tunnel excavation is a highly sequenced and repetitive process. We cut the rock, install our support, then move forward and we cut again. And once we've excavated, rock reinforcement needs to be installed. This is commonly in the form of rock bolts, cable bolts or rock anchors, and they work by strengthening the rock mass surrounding the excavation to enable loads to transfer around the circumference of the tunnel. They also help to restrain rock wedges within the rock mass. Once our rock reinforcement is installed, we spray a lining of shotcrete that is used as another primary support measure to restrain smaller wedges between the rock bolts and support the arching effect of the tunnel. This shotcrete combined with rock reinforcement provides a stable tunnel excavation that allows the excavation works to advance. In areas of poor ground conditions, such as fault zones or low cover areas, we may have to look at adopting heavier primary lining systems. Lattice girders, or heavier steel sets, are a support system that can be used in areas of weak rock fault zones or low cover. Additionally, the installation of spiling bars around the crown, which is the top arch of the tunnel, can be used in areas where the strength of the surrounding ground is insufficient to provide the necessary support. Where these spiling bars are not strong enough to provide the required support, we can install canopy tubes, which are steel tubes drilled into the ground above the tunnel crown to act as a canopy above the tunnel. This is also often called a pipe umbrella. You can see the installation of one of these canopy tubes occurring in the image. Once installed, the tube is grouted or filled with concrete to provide the necessary support for the excavation to proceed below. After our primary lining is installed, we need to install waterproofing measures where required, and then our final or permanent tunnel lining. Waterproofing is usually achieved through the installation of a sheet membrane where a cast in situ final lining is used, or as a spray-on membrane when a Shotcrete final lining is proposed. In our TBM, our permanent lining is achieved from the installation of our precast concrete rings. These precast concrete rings have a rubber gasket between them, which seal the rings, also providing the waterproofing function. In a cast in situ lining construction, sheet membranes are manually placed, pinned and welded together from a specifically designed moving scaffold. The casting of a kicker at the base, which serves as a foundation of the arch lining, is placed, and then from here the installation of the lining reinforcement is placed if required. Once complete, a lining formwork is moved into place, and then the lining is cast behind this. In a TBM, we use a segmental tunnel lining, which consists of precast concrete segments installed in a ring, which is assembled by a vacuum lifter located on the TBM. These rings consist of precast concrete segments which connect in a predetermined arrangement and avoid joints in adjacent rings from aligning. The segmental lining of a TBM also provides a construction purpose, as the TBM can thrust off the completed ring to advance its cut ahead to the next round of the excavation. Permanent linings need to be designed to accommodate not only the external loads of the tunnel, such as groundwater and development above the tunnel, but must also be designed to account for loads within the tunnel, such as the installation of mechanical and electrical plant, internal structures, and in the case of Cross River Rail, our future train loads. Waterproofing of a tunnel can be designed as either a drained or an undrained, which is also known as a tanked tunnel. In a drained tunnel, waterproofing is applied to the lining and water is collected from this. The water is channeled by means of strip drains or dimple sheets into a tunnel drainage system. Because of this, the permanent lining does not need to be designed for a full groundwater load, which makes drain tunnels less expensive. But the disadvantages of a drain tunnel are that the drainage system needs to be sized appropriately for this total volume of water. A drain tunnel will also lead to the permanent drawdown of the groundwater table surrounding the tunnel, and this could result in ground settlement or other impacts. The construction of a tanked or an undrained tunnel requires sealing the entire tunnel by installing a complete waterproofing system. This will eventually allow the surrounding groundwater level to restore around the tunnel, but the lining will need to be designed to account for the full groundwater load. This will make an undrained or a tanked tunnel more expensive to construct. There are 16 permanent cross passages in the Cross River Rail project. A cross passage is a passage connecting between two adjacent tunnels. This image shows our first excavated cross passage on Cross River Rail. Cross passages are there to provide a means of access and egress for adjacent tunnels for evacuation and emergency services intervention in the event of an incident in the tunnels. But they also provide a space for mechanical and electrical plant and fire and life safety systems to be installed along the alignment of the tunnel. A cross passage opening will weaken the main tunnel structure in the junction area, and increased support in this intersection area will be required. In some tunnels, the opening of the main tunnel for a cross passage construction may also be preceded by advanced grouting works or activities such as ground freezing, which are needed to provide sufficient support around the excavation until the primary support system can be installed. Cross passages can be constructed with a variety of techniques, such as road header, drill and blast, micro TBMs, or rock hammers. Ventilation is a key aspect of tunnels, and tunnels need to be ventilated. The bigger and longer a tunnel, the bigger the ventilation requirements will be. During construction, dust needs to be extracted to provide fresh air and to protect the crews in the tunnel from excessive dust inhalation, fumes, oxygen depletion, and heat. So separate systems for air supply and air extraction must be provided. This extracted air must also be treated before it is discharged to the atmosphere, so large units known as scrubbers clean this air prior to its discharge. In the permanent use case, the ventilation system needs to be designed to suit the use of the tunnel. The ventilation requirements for a vehicle tunnel, which must safely deal with vehicle emissions and potential large fires in the tunnel due to hydrocarbons, are significantly more than the ventilation requirements that are needed for a rail tunnel that only carries electric locomotives, or for a water supply tunnel that is not a generally occupied space. For the Cross River Rail project, 1.4 million cubic metres of spoil needs to be excavated and removed. So you can see that spoil removal and treatment is also a large consideration when it comes to tunnelling. For the road headers on Cross River Rail, we are transporting the spoil to the surface using trucks. For the TBM, we have a dedicated conveyor system to each TBM that is conveying the spoil all the way from the excavation face to the spoil shed at the surface. As the tunnel approaches our northern portal, we will have over 14 kilometres of conveyor belt deployed on the project to facilitate this spoil transfer process. Once within our spoil shed, which is provided at the Woolloongabba site to manage dust and noise associated with spoil management activities, the spoil is loaded onto trucks and driven to a number of disposal sites across Brisbane. These sites include Brisbane Airport, Swanbank, Pine Mountain, Larapinta and the Port of Brisbane. Given that tunnelling works often occur below residential properties, major roads or CBDs, the ongoing monitoring of a tunnel excavation is a highly important task. By constantly monitoring the behaviour of the tunnel and surrounding rock mass, we can determine that the ground is behaving as expected or implement additional support or controls in the event that monitoring results are showing something unexpected. Each tunnelling project will have a detailed monitoring plan which outlines the installation and monitoring requirements for movement within the tunnel and on the surface. Trigger levels are set for all works, which indicate pre-agreed levels of movement that require further investigation and possible intervention works. The instrumentation used to record the movement of the ground includes monitoring prisms, extensometers, inclinometers, and vibration monitors, which are installed on adjacent structures or utilities where required. Groundwater monitoring is also carried out to observe changes in groundwater levels, as well as the monitoring of surrounding groundwater quality. This is to ensure that the works are not having any detrimental effects on the environment. Fire safety, as mentioned before, is an important consideration not only for an operating tunnel, but also during construction. Given that tunnels are underground and it is often a long distance to the nearest exit, the provision of appropriate fire controls and safe evacuation methods is of utmost importance. This applies both during construction for the workforce and also during the operational phase of the tunnel, when the general public will be occupying the tunnel and are unfamiliar with the tunnel environment in the case of an incident. To address this, regular egress points must be provided, generally in the form of cross passages, and clear and consistent signage and evacuation messaging must be provided throughout. Emergency evacuation and exit schemes need to be in place for all stages of construction, and these continue through to the operational phase, when detailed intervention plans are developed and workshopped with emergency services. Mock incidents are also run to provide tunnel experience and training for first responders. During construction, tunnels implement a tag in and out procedure so that at all times the occupants within a tunnel are known. On Cross River Rail, this system has been automated with the use of sensors which track and record tunnel entry and exit of personnel. Providing a safe tunnel, though, starts at the design stage. The safety and design process is mandated on all Australian projects and requires the risk assessment and mitigation approach starts at design. This is where the future risks for construction or operations can best be managed, often by changing the design now to eliminate a risk from being realised in the future, or where it cannot be eliminated, mitigated to a point where it is considered acceptable. The safety and design process consists of workshops around design packages that identifies and evaluates hazards for likelihood and consequence prior to and after the introduction of the mitigation measures in accordance with an agreed risk matrix. The risks considered must not only be design focused, they need to consider the whole of life of an asset. Hence, safety and design workshops need representation from all parties, including designers, contractors, operators, maintenance teams and asset owners. The permit to tunnel process was developed over 15 years ago on the EastLink project and has been used on Australian tunnelling projects since. A permit to tunnel is required for each excavation and is typically valid for a certain chainage or section of the tunnel or over certain dates and times. No excavation is allowed to proceed without a valid and signed off permit to tunnel. This permit to tunnel is an instruction outlining all requirements during the time frame of its validity. It considers the appropriate tunnel support class to be installed, the length of advance, and the requirement to install monitoring devices, and will also review results from installed monitoring devices to ensure that the tunnel excavation is behaving as expected. Where required, this PTT or permit to tunnel may recommend a change to support type or the installation of additional monitoring to address changing ground conditions or in the presence of unexpected ground movement. So there is an overview of how the approach to designing and constructing a tunnel is. So now let's look at specifically the Cross River Rail's year of tunnelling. Both our TBMs are now operational. TBM Elsa has completed over 400 metres of her journey and she is quickly approaching her crossing of the Brisbane River. TBM Merle has just launched this month, but she has already excavated over 50 metres. Our two road headers driving south to Boggo Road have both achieved over 100 metres on their journey, including the excavation of our first cross passage on the project. At our Albert and Roma Street stations, excavation of the station caverns continues in anticipation of receiving the two TBMs later this year. And at Boggo Road, excavation of the cavern there has just commenced in anticipation of the road headers arriving later this year also. This video will give you an idea of the TBMs being assembled at the Woolloongabba worksite. So there's just a quick overview of the TBMs being assembled. That was TBM Elsa. And to wrap up on everything that I've discussed today, here is another short video that will give you some more insight into how we at Cross River Rail are tunnelling under Brisbane in 2021.
Cross River Rail spans from Dutton Park to Bowen Hills. It includes twin 5.9 kilometre tunnels and 4 new underground stations. Machines called road headers will excavate tunnels between Woolloongabba and Boggo Road. The 4 new station caverns and cross passages every 240 metres. Moving on their bulldozer-styled tracks, road headers are electrically powered and very manoeuvrable. Their pineapple-like head is fitted with metal picks. They rotate, break up and excavate the rock. A conveyor system transports the rock to the back of the machine, where it's then transported to the surface. The tunnel is completed by installing supports called rock bolts and then sprayed with Shotcrete. Road headers seem huge, but they're dwarfed by the project's 2 massive double shield tunnel boring machines, or TBMs, which will excavate the Cross River Rail tunnels from Woolloongabba below Brisbane CBD through to the northern portal at Spring Hill. At the front of the TBM is the cutter head, where cutting discs roll on the tunnel face, breaking rock harder than concrete, which is then passed back to the conveyor. Travelling up to 20 metres per day, the TBM progressively lines the tunnel with curved concrete segments. A crew of up to 15 will monitor works around the clock, ensuring smooth operations on the TBM's 3.6 kilometre journey, accurately aligned with state-of-the-art navigation systems.
So, wrapping up, by the end of 2021, all 4 underground stations will be excavated, and we will have our twin tunnels dug through to the northern portal and also to the southern portal. Major construction activity will also be underway at Exhibition Station, and works will be happening at Yeronga, Fairfield and Yeerongpilly. In addition, works to support the implementation of the European train control system will be underway, and will be starting to do pilot line testing. If you would like to know more about the TBMs, I encourage you to join my colleague Ty's presentation, which is on tomorrow from 5 to 6 p.m. and is entitled Meet the TBMs. And if you would like to know more about Cross River Rail, you can visit our website at www.crossriverrail.qld.gov.au. From here, you can subscribe to email updates about our project, or if you're social media savvy, we have plenty of platforms there that you can sign up to and get regular updates. If you're more a hands-on person, you can come down to our Cross River Rail Experience Centre in Elizabeth Street, where we have lots of interactive activities to learn what is happening on Cross River Rail. And if you're along the alignment, we often have community consultation or community events. So if you see one of these pop up, feel free to come along and say hello. Thank you for your attendance today. I hope you learnt something and had a good time.